So the architecture for the microcontrollers, there are two different architectures. One is called von Neumann and the other one is the Harvard architecture. So in the von Neumann, instructions and data are stored in the same memory. So you have one bus between a processor and the memory. But in the Harvard architecture, the instruction memory and data memory are separate. So you have two different buses between processors and memories. So this is more efficient or faster. So this is the block diagrams for these von Neumann and Harvard architectures. As you see, in the first case you have only one bus which is used for the data and instruction, but in the Harvard you have the instruction has a separate bus and the data has a separate bus. So if you look at the ARM architectures, so Cortex M3, M4, M7 and M33, they are all using Harvard, and the low performance Cortex M0, M1 type of architectures, they are using von Neumann architecture. So let's look at the levels of our codes. For example, we might have a high level language such as C, right? So this is a code written in C. So this is much better, easier to understand and easier for us to write and maintain and use it for in some other codes as well. So once we compile this code, then the compiler will give us some assembly program, right? So it will just give some textual representation of instruction, right? It will be saying some move some numbers, so do some kind of branching, add numbers, compare them, and etc. But once we use this assemble, then we will be getting the machine program. So this is all ones and zeros. So this is very hard for us to understand, but it is easier for the machine to execute, right? So these are basically encoded instruction and data, right? So all this information has been encoded in this machine program. So as I said, so we have these high level languages such as C, C++, and then one lower level is assembly language, and another lower level is this instruction set architecture or machine language for our microcontrollers or hardware, and then the lowest level is our digital logic, our gates and etc., right? So which performs all these operations. Like, as you go lower, it is harder to understand, right? So it is much better for us to write our code in the high level language. So this is assembly language is one step up from the machine language. So it is originally, before the high level languages, it was a more user friendly way to program. So now it is mostly a compiler target for our language compilers such as C compiler, C++ compiler. So this is an example of a assembly instruction. So we have this opcode or operation code. It tells the processor what to do with the data, and we have our operands, where to get the data and where to put our results. So now we'll see an example how a program runs. So let's assume we have a simple program which has this A and B variables, and then we add these two variables and then we store it in a C variable. So this C code, once you compile it, the compiler will give you an assembly code. So it will have some instructions. So it is saying move 0 to R1. So this register 1 is actually storing variable A. R2 is storing variable B. So it's saying move 1 to R2. Now it says add R1 and R2 and store the result in R3. R3 is basically storing the variable value for C, and then it is setting the return value of 0 to R0, and then it is doing a return operation in assembly code. So after the assembler, then it will generate you a machine code in binary, and this will be executed by our processor, right? And this machine code is also can be represented in hex. It is easier for us to write it in hex. Basically, this is what is executed, and this is the operation it does in assembly. So the processor also has some registers that we set. So the processor needs to store all these variables. So it has some general purpose registers from R0 to R12, and each of these registers are 32 bits. So these are called 0 to 7 is low registers, register 8 to 12 is called high registers, and we have also some special purpose registers, right? So this is stack pointer, link register, and program counters that we will be learning about these as well. So why the processor needs registers? Because it is fastest way to read and write, right? Instead of going through the memory and read a value, it might be easier for the processor, as these registers are inside the processor. It gives us fast way of writing and reading because they are within the processor chip. Okay, so these number of registers changes from one chip to another, but usually even in our lab we have 0 to 12, 13 general purpose registers, and R13 is called, as I said, stack pointer, R14 is the link register, R15 is the program counter, and we will be learning about these, right? And these some more special registers such as MSP and PSP, right? We will be also learning about these. So once you execute an instruction or a program, we go through 3 steps. The first step is we fetch the instruction at the program counter register. So the program counter register holds the memory address of the next instruction, right? The processor needs to know where is the next instruction, and it stores the address for the next instruction in this program counter. And once it fetches this instruction, the next thing it will do to decode the instruction. It will decode and understand what to do, and the third step it will execute the instruction. For example, this is our memory, and now our program counter is storing this address, right? Hex 001B0, and then it is telling the processor go to this address and fetch the instruction, fetch this instruction, decode this, and execute it. So once the processor does this fetch, decode, and execution, it does a pipelining, meaning, let's say in the first clock cycle it is doing a instruction fetch, and on the next clock cycle it is decoding this instruction, but at the same time the processor can go to the memory and fetch another instruction, right? And on the third clock cycle, while it is processing the instruction I, executing the instruction I, at the same time it can get decode the instruction I plus 1, and at the same time it can fetch another instruction called I plus 2. So in a way it is doing these 3 operations at the same time using this pipelining, right? It does not wait until execution. If it doesn't use the pipelining, it will first execute, it will first process these 3 steps, and then it will do another instruction fetch here, another decode here, another execution here. So but it will be slow, right? But using this pipelining, while it is doing execution, at the same time it is doing a decoding, at the same time it is doing a fetching. So all of these are done by separate circuits, right? So you don't have to wait until one is finishing, right? So you can do 3 of them at the same time. Any questions here? Process these 3, right? Fetch, decode, and execution. So one way of doing this, you can do fetch, decode, execution, another fetch, another decode, another execution. So, but in this case, the second part will be, you will be doing it here. But instead of processing the next instruction here, I can, because the fetch, decode, and execution are done by different modules. Okay, so if I don't use the pipelining, if I am doing a fetching, the decode is not working and execution is not working. So the decode will be working here and execution will be working here, but the fetch and decode, let's say if I am executing here, the fetch and decode will not be doing anything, right? They will be just sitting there idle. But instead of to make it more efficient, what I can do, I can, while executing this instruction I can make sure my decode module is decoding the next instruction. At the same time, my fetch module is fetching another instruction, so that it will be more efficient. Now, at 1 clock cycle, I am doing 3 operations. But if I don't do pipelining, I will be doing another fetch here, another decode here, another execution here, which will be slower. Okay. So let's see an example how these machine codes are stored in the memory and executed. Okay, let's see. Initially we have this is our CPU. Okay, and inside our CPU we have our registers, and we have our arithmetic logic unit that does the operations, and we have a memory, okay, that stores our instructions. So let's say my program counter, which holds the address of the instruction to be executed, it is pointing to this address, right? So this is my address. So this program counter has this address. It means it's pointing to this memory location. So I need to go get this instruction. So I will be getting 2100. Okay. So this is an instruction. Once I decode this instruction, it says move 00 to register 1, right? I decode my instruction and it tells me I need to move 00 to my register 1. So what will it do? Now I need to execute my instruction, right? Once I execute it, I will be storing 00 on this register, right? Okay, so we moved 00 to our register 1, right? Now what you see, now my program counter is pointing to next address, right? So this is my next address and this is my next instruction, right? I finished execution of first instruction. Now I need to execute the next instruction. So the next instruction is this one. Okay, let me see what happened. Okay, so this is my program counter. This is the first instruction, 2100, and then I increase my program counter by 2. So it goes to the next instruction, which is 2201, and this, if I decode this instruction, it tells me I need to move 1 to R2. So I will be moving actually 1 to R2. So now I execute it as well. So it says decode and execute. So now my register R1 has 0, R2 has 1. Now I will be increasing my program counter, right? So my address has increased. Now as you see, it is now pointing 1B0, and my next instruction is this 188B. So if I decode 188B, it means you need to add R1 and R2 and then store the result in R3. So if I execute this, if I add these two, so I send this register 1 and 2 to the arithmetic logic unit, right? And I add them, I tell the ALU you need to do an addition, I add them and I store it in the R3, right? Then you will increase your program counter. Now the next instruction is 2000, right? It means move 0 to R0. So it already has 000 here. And the next instruction is branching. So you need to return to link register, and we will be learning this return and link registers later. So you will be completing your execution, right? So this is the last instruction for that C code that we had. Any questions here? So this is a very basic example how we run our CPU and get some instructions from the memory and execute them. So let's see, we are trying to calculate the sum of an array. I have an integer array with 10 locations, and these are the data in this a variable, right? And I am doing some adding all these array contents, right? So basically what we will be doing, so we have some instructions, right? These are our instructions for our code. So we will be storing these instructions in the read-only memory or in the flash memory, you might say, okay? And there is also some data section. So this is our data, right? These are not instructions, these are the data we need to process. So we will be putting them inside the data memory. So for this memory, it might be starting from the memory address might be this. For this RAM, the memory address might be starting from this address. So we have different addresses for this read-only memory and RAM memories, okay? So basically, if you look at the instruction memory, this is what you store. So given this code, this is what you store inside this read-only memory, right? And then these are basically the instructions for this code. This is what you need to do, right? So basically you are storing these instructions inside this read-only memory. But if you look at the RAM memory, right, these are all this data inside this RAM, right? So for example, the memory address is starting from hex 20000000, right? So we have this A0. So this is my A0. So this is my A1. This is my A2, A3, right? And these are its addresses, right? So, and each variable in this case, each location is 16 bit and each variable is 32 bits. So this is my one variable, this is another variable, and this is another variable, right? If you look at the addresses, it is byte addressable, right? So I have 2 bytes here, and the next addresses you increase it by 2, and the next addresses you increase it by 2, right? Because in each location we have 2 bytes. Okay, that's why the address is increased by 2 here. So as you see, all of them is in hex. And then the total variable is stored here, right? We process it and then we will be storing the result, the total, here. Any questions? So actually for the processor, you can just say the processor has the memory, and then the SRAM memory and the flash memory has different regions in your memory. The start addresses are different for these two types of memory. And this is the instruction part that goes to the instruction memory, and then these are going to the data memory. Okay, so there are different parts in the SRAM as well. So there are some zero initialized data section in the memory, for some another section for the initialized data. So these are different types of data. Okay, and then we have also stack in our memory. We will be also learning about this. So we will have a stack pointer. So while we are doing some functions passing, we will be putting our variables into the stack. So, and then there is a heap start address and stack pointer, which for the stack to track our data in the stack, and also the stack start and stack end, and heap start and heap end. So we will be there are different sections inside the RAM. So we will be seeing these later on. And this is called a memory map in the in our microcontroller, right? For the processor, every module has a memory address, right? So RAM, external RAM might have a address from starting from one location and ending in another one. Another device might have another addresses. Okay, so it might have some peripherals. The addresses of the peripherals might be different. Okay, so this is called a memory map for the processor. So for the processor, every device has an address, and then if it needs to communicate with that device, you need to provide it to the address for that device. Okay, so this was the basic concepts and a simple example for our processor, how to run, how to do decoding, fetching, decoding and execution. Okay, so later on we will be learn about more on the architecture of our processor, and more examples for the assembly languages and interfaces, etc. So do you have any questions regarding this lecture? So don't forget, next week we will be starting at 10 a.m. Okay, if you don't have any questions, I'll see you next week. Okay.